One. Dear Lord Jesus, let this go well. Okay, which one? 17 and 19. 17. Hot July moon. Water is flowing at the rate of 50 cubic meters per minute. So I already know I have dVdt here. How do I know that's dVdt? Why does it keep my hand keep? How do I know that's dVdt? I know it's a rate. That's right. The cubic meters gives me a hint that that's going to be a volume type thing. All right. So water is flowing at the rate of 50 cubic meters per minute from a concrete conical. There's conical again, y'all. Reservoir. Can't say it. Say it. Reservoir. Okay. I can't say, I don't know why I can't say that word. It's kind of like rural. I've never been able to say that word either. No, I can't say it. I can't get my R's to do, so that one must, okay, anyway, it doesn't matter. Concrete conical container. Here we go. Vertex down. Base radius, 45 meters. But my base is actually up here. So 45 meters. Let me know if this is not how you did yours. And then the height of 6 meters. Wow, this is not accurate at all because it's definitely way wider than it is high, but that's okay. How fast is the water level falling when the water is 5 meters deep? So what we want is fast is the water level. So the water level would be the height, right? So we want to know how the height is changing with respect to time. Did y'all get that? And it says for that when, what did it say? When the water is 5 meters. All right. Here's what we have. Now what do we know? Do we know how to find the volume of a cone? We do. What's the volume of a cone? I'm going to have to write one variable in terms of the other, it looks like. Would you agree? In other words, set up a ratio like I did before. Is that what y'all did? Yes or no? Maybe so. Thank you, Caroline. So 45 over 6. So that's my radius. My radius over my height should always be well, your R won't be, if I'm down here, my R would be different. You see what I'm saying? So I'm pouring water in this way and it's filling up this way. How's it going out? It is going out. It's not going in. This is going pouring out. Yeah, so it's going down. So it should get a negative. Well, because I'm looking at what I have, I'm looking at what I need or what I want, and I've got too many variables in here. In other words, if I take the derivative as it sits here, I'm right. And so I'm not going to be able to do that. So what shall I do? I want H. So what does R equal? Can I write R in terms of H? Yes. So R 6R equals 45H. So R equals 45 over 6H. Is this what y'all did? This is how you did it? Does that go in evenly? No. Divide them both by 3 maybe. 15 over 2. Are y'all with me or no? Do you agree with me or no? Okay. I'm going to rewrite this volume equation to have only h's, 1/3 pi. It's not r anymore. It's 15/2h squared. 1/3 pi, let's see, 225/4 h cubed. I'm going to go ahead and put those two together. $75. Is that right? And then the 75/4 reduce? I feel like no. I feel like I should use a calculator. No. Okay, so I got 75/4 pi h cubed. That's my volume. Now what? Derivative dv dt equals, I'm going to multiply that around, so 3 times 75/4 pi h squared dh dt. Plug in what you know. What do I know? dv dt, which is 50. Yep, because it's straining out. You're right. Look at y'all. Good job. Wow, and it didn't even tell y'all that, and you got it. Good job. 3 times 75, so that would be 150. 150 plus 75 would be 225. Is that right? 225. Does that reduce? 225/4 pi. H was 5. I'm just plugging in what I know now. pH dt. And solve it. $25 times 225/4 is a gross number. We'll multiply by the reciprocal. 4/5625 times 50. I got -8/225 pi. That is not at all what they got. Oh, okay. So if I put that in centimeters, do I get what they got? No, you can leave it. It did say. Okay, 32/9. If you multiply that by 100 to get it, it'll be in 8/25 times 100 would give you 32/9, and that's your centimeters per what minute. So I would be okay here if you said bless you, meters per minute. But if they ask you if you want to know why. Ooh, I'm glad we got that one right. Thank you, Lord. Okay. Does that make sense? And then B says, how fast is the radius of the water surface changing at that moment? Oh my goodness. Okay, so part B. How fast is the radius? So this time I'm looking for dRdt. So I could use what I already have, right? That's what Abby was telling us yesterday that I think you did with that one problem. Use what you already had. Find the derivative, find dv dt with both variables, or you can go through this whole process, but instead of solving for r, you solve for h and you rewrite this. right? So whichever way you want to do it, it doesn't matter. Which way did y'all do it? Or did you do it? Y'all didn't do it. Oh, I see. Yeah, that's what she was saying. That's smart. That wouldn't have worked the first time. Okay. So if R is 45 over 6H, that means dr dt equals 45 over 6 dH dt, right? We couldn't have used that the first time because we didn't know either one of those is why. But now that we know one of the two, you're absolutely right. We could use that. So I'm going to plug in. And if I use this one that I've already converted, I don't have to worry about converting again. Negative 32 over 9 pi should give me dr dt. So dr dt is, calculator, 45 over 6 times 32 over 9, 80 over 3, 80 over 5 centimeters. Smart. I was about to do one more work. Are y'all okay? Gravy? Okay, and then you said 19. The infamous falling ladder problem. Yay, day. We're going to have to use a trig function on this. I see it coming. Shadows, falling ladders. Here's my building. They even drew a nice picture for you. This ladder is sliding down this way, I'm assuming. I haven't even read the problem, but I'm assuming this is what's happening. This is 13 feet. The ladder's not changing, right? So that's going to be a constant. X of t. But it is sliding down and sliding over. All right, a 13-foot ladder is leaning against a house. See the figure when its base starts to slide away. By the time the base is 12 feet from the house, so I'm looking at when this is 12. The base is moving at a rate of 5 feet per second. I'm not going to put this here. I'm going to say B is. Ooh. Okay. How fast is the top of the ladder sliding down the wall at that moment? I guess I can put that. All right, tell me what to do. I'm looking for. You're looking for what? Right. So we'll call. What'd you call it? H. A. Okay. Call it A. So we need A. Because it asked you how fast is the top of the ladder sliding down the wall at that moment. So how fast, this is my ladder, right? How fast is it sliding down the wall? So that would be the rate of change of A. Yes, so imagine the ladder propped up against the wall, and as it slides out, it goes down the wall and it goes over across the ground, right? Does that make sense? It's doing this. Kind of slides. Okay. I think Pythagorean theorem would be our friend here. We know that a squared plus b squared equals c squared, with this being a constant. It's a constant because the ladder's not growing any longer, right? I don't know how to pause that right now. All right, so We have dB dt, we need dA dt. We've got b. So I think we just take the derivative now. Agree? 2a dA dt plus 2b dB dt equals 0. Why does it equal 0? C is a constant. It's not changing, right? There is no rate of change there. Let's plug in what we know. We know that, what do we know? We know dB dt is 5. We can solve for a to find out what a is. You're exactly right. 12 squared plus a squared equals 13 squared. Thank you. So a is 5, b is 12. I'm down to one variable. I can do this from here, right? I have 10 dA dt plus 120. Does that make sense? So now I have 10 dA dt equals negative 120. So what is dA dt? Does it make sense that it's negative? Why? Because the ladder is sliding down. That's exactly right. Y'all good? You sure? I always ask if y'all good and you're always like that. I don't ever believe y'all. No, I'm just kidding. I do. At what rate is the area of the triangle formed by the ladder, wall, and ground changing at that moment? So now we're changing to, we need the area, the rate of change of the area. Well, how do you find the area of this triangle? 1/2 base times height, and the height is a. Agreed? Let's see. Again, I have dB dt, and now I know dA dt, so I can just take the derivative here. 1/2 derivative of the first times the second plus the first times derivative of the second. Do I have enough information to plug in here? Yes, I absolutely do. dB dt is 5. A we said is 5 also. B is 12. And dA dt is what we just found, negative 12. So we get 1/2 25 minus 144, which is what? So negative 59 over 2? Or you did the 1/2? That's fine. We'll leave it there. Negative 59.5 feet squared per second because it is area. Everybody okay there? I'm going to guess that part C is what threw you. So part C says, at what rate is the angle theta between the ladder and the ground changing at that? Any guesses what we need to do? Look at there. All right, so now I need d theta dt. So I need an equation that's going to relate d theta dt to something that I already have. And I have a lot of stuff already, right? So there are various things that I could use here. Adam says pull out a sine or use a sine. So did you do sine theta? Adam, is that what you did? Oh, okay. Use what? Tangent. I would use tangent. Well, I guess you could do. Doesn't really matter. Opposite over adjacent. Oops, I didn't mean to put, yeah, no. There we go. Wonder if it would work. I might would use, I think I'm going to use sine or cosine. Can you use sine or cosine here? Do you see why I'm thinking maybe? I don't see why we couldn't. Okay, the reason I would go with sine or cosine is because they'll use the hypotenuse, and what's special about the hypotenuse? It's a constant. It's a little easier to work with. That's the only reason I would. I don't think it's wrong if you use tangent. I don't think it's wrong. I think you can pick whichever one you use. I'm just reasoning through what I think will be. All right, let's do this. Sine theta equals opposite, and the opposite is a over that constant, right? So I'm going to go ahead and take the derivative, and the derivative would be cosine theta d theta dt, because I have to chain it, right? I don't know what theta is, equals, and then I do 1 over 13 dA dt. Now, at this moment, could I figure out what theta is? Yes, I have enough information to figure out theta. Do you agree? At the moment when A is, what did we figure out A was at this moment? We found it some 5. Well, because it's not a constant, so whenever I take the derivative, I need that rate of change in there. But the 13 was a constant, and it's not going to change, so that's why I did that. So if I multiplied by dB dt, I would be multiplying by 0, which is okay. The cosine. Now I'm going to use what I know. The sine is a over 13, so I know that sine is, at this particular moment, and only at this moment, it's 5 over 13. So I can do the inverse sine of 5 over 13 and find out what theta is. Probably need to be in degrees for this, I'm going to guess. No, we can do radians. The answers that they gave us in radians. So we can do radians, that's fine. So what is, actually, stop, I'm being stupid. I'm being really dumb. Do y'all see what I'm doing? Wrong? I'm doing way too much work. Look at that triangle. What's the cosine of theta? What's the cosine of theta? Look where theta is. Look at my triangle. What's the cosine of theta? Say it again, Chris. 12 over 13. Adjacent over hypotenuse. I don't know why I'm doing all that like an idiot. Right? Cosine theta is adjacent over hypotenuse. I don't have to go through, I don't have to know what theta is. Theta, it doesn't matter. One over 13, and what is dA dt? Negative 12. That was really dumb. Okay, 12 over 13, d theta dt, negative 12 over 13. Multiply by the reciprocal, they're exactly the same. So if I multiply by the reciprocal, what is d theta dt? Negative 1. Only this time, let's think about this. My theta is in radians, or, well, we used radians here. Yeah, radians. Per, what? Second. I was fixing to make that infinitely harder than it was. That one was fun. What else? I can't remember what y'all had. Part B of 21. Hauling in a dinghy. A dinghy is pulled toward a dock by a rope from the bow through a string through a ring on the dock 6 feet above the bow. Bow or the bow? Bow. The boat. The bow. As shown in the figure, the rope is hauled in at the rate of. Okay, so I have another triangle. This is my theta. This is 6 feet. They were nice enough to draw us a picture. The rope is hauled in. Where's my rope? This is my rope. I'm going to call it C. 2 feet per second. And part B says at what rate. We probably have to do part A to get part B. I'm going to guess. How fast is the boat approaching the dock when 10 feet of rope are out? So I'm looking for this. I'll call this A. So I need dA dt. Again, my 6 feet is a constant. That dock is not changing its height no matter what we do with the boat or the dinghy or the rope, whatever it is we're talking about. So, okay, so I know that A squared plus B squared is equal to C squared. This is the rope. This is my constant, right? Yes. So if I take the derivative here, I have 2A dA dt plus 0, because that's a constant, remember. Derivative of a constant is 0, equals 2C dCt. I have, let's see, what do I have? Am I going to have to rewrite this in terms of something? I have dC dt. Oh, when there's 10 feet of rope. So this is, I didn't read that part. C is 10. So you're right, I can solve for A. So A squared plus 6 squared equals 10 squared, which tells me that A squared was 100 minus 36, 64. So A is 8. That's nice. dA dt is 2. Negative 2, right? Is it negative 2? It's the rope coming in or going out. Dinghy is pulled toward a dock by a rope. So it's pulled toward, so I'm losing rope, right? So I'm going to do negative. Because that length is getting shorter, right? So I have negative 32 equals, no. What am I trying to find? I put that in the wrong place. I put negative 2 in the wrong place. This is negative 2. This I don't have. This is what I'm looking for. So I have 16 dA dt equals, what was C? C was 10. Negative 40. So dA dt is negative, as it should be, right? Because I'm losing that distance. 40 over 16, which is 10 over 4, 5 over 2. So what y'all got for part A? I know y'all didn't need part A, but I needed to work it so I could understand part B. Okay, so now part B was your question. At what angle, at what rate is theta changing? What's wrong? Did I do something wrong? Oh, I see what you're saying. Because it's saying towards the. I look at it as a triangle losing distance. It's allowed. Either way. Um, but they do have a negative for part B for theta. I guess because theta is decreasing. Okay. At what rate is the angle changing at that moment? So again, I'm gonna need and I'm at this same moment, right? So since I'm at this same moment, I can kind of put in what I know. I know that dA dt is -5/2 feet per second. I know that C is 10. I know that A is 8. And so now all I need is d theta dt. So again, I'm probably going to choose one that has a constant to do my trig function. So I have, what side is that? That's adjacent. So tangent or cosine? I'm probably going to go with cosine. Cosine theta equals 6. That's my constant, right? Over hypotenuse, which is not a constant, so I'm going to put C in here. That way I can get that rate in there as well. All right, so that would be negative sine theta d theta dt equals 6 times, this is on the bottom, that's really like 6c to the -1, right? Tangent might have been easier on this one. It's okay. We will plug in what we know. We know that the sine of theta, here's theta, sine is opposite, which is 8, over hypotenuse, which is 10, but it's negative, so -8/10 d theta dt equals -6 over, what did we say C was? 10? And dc dt is -2. So what y'all got? Or y'all didn't get this one? Did not get this one. Sine of theta from that triangle. I'm going to go 6 over 50, and I'm going to multiply by the reciprocal. Let's see. 5, 4, 3. 3 over 20, negative. I hope that's what they got. Radians per second. I feel like this is boring, y'all. You think this is not as bad as optimization? I look back. It says it in there, so I can check. Okay. Well, I'll give you the harder ones now then. Okay, but that's okay. We started out easy and we're kind of working our way up. But I'm gonna give you some time to work today. Let's do these. Won't be due until Friday whenever I come back, and I'm just gonna leave you some videos tomorrow, and then let you work together on this tomorrow as well. It was, but Miss Goodwin wanted today. Miss Goodwin and I both have days, and she wanted today because she's introducing something in her. Are y'all in her AP class? AP what? Okay, that's yes. And she said she has to teach that, and she's got to do it Thursday. She couldn't do it today and then leave y'all a day or something. I don't know. So she asked me if I'd swap with her, and I'd do Thursday. So yeah, and I just keep chugging along. There's not really anything that I do that like that. I don't know. I don't teach anything that sounds nearly as complicated as metaphysical poetry. That sounds a bit intimidating. No, that sounds like what she said. All right, so this will be due Friday. I'll let you use tomorrow, so it'll be a little more than usual, but this will be our last practice. I'm also going to leave you a couple of videos on College Board to watch. Related rate or optimization, maybe a couple of both. Related rate and optimization. They're not long though, and they're really helpful. Let's do. All right, 22 actually starts on 265. 22. Okay, now here's where we get to the little bit harder ones. 31 to 33. And then if y'all get that one, I'm just going to quit teaching. Let y'all just go ahead and take the exam. That's it. So don't get overwhelmed with it. It'll take you through today and tomorrow, and then you'll be ready, I think. I did. You didn't see it? Oh, okay. Yeah, I did. I think that's enough for 2 days for y'all, for today and tomorrow. Plus a couple of videos. A couple more, you think? And I am going to go ahead and assign, so make sure y'all log in tomorrow to AP Classroom. That's what I was trying to say, and I was College Board.